and welcome to the Chemistry channel. So today we're going to be talking about Hess's law, which is the second method used to determine delta H of the reaction, or heat of the reaction. So let's first remind you of enthalpy. So recall that enthalpy, this is enthalpy, is a state function. And remember that a state function is only dependent on the final and initial states. So if you were to integrate a state function, you would get this. So in other words, the change in enthalpy is only due to the initial and final states. So in other words, because enthalpy is a state function, it is path independent. So in other words, it does not matter how you get there. It only depends upon the initial and final states. So therefore, enthalpy is path independent. It does not matter how you get from the initial to the final state. It only depends on what the initial and final states are. Now, because enthalpy is a state function, we do not need calorimetry to determine the heat of reaction. So that's heat of reaction. So we do not need calorimetry in order to determine the heat of reaction. We can use tabulated heat of reactions from known reactions in order to calculate our reaction of interest heat of reaction. So we can use already known heats of reactions from known reactions in order to calculate our reaction of interest heat of reaction. And this is the fundamental principle of Hess's law. So Hess's law states that if a reaction is carried out in multiple steps, then delta H of the reaction is equal to the sum of all the delta H of reactions from each individual step. So Hess's law states that if a reaction is carried out in multiple steps, then delta H of the reaction, or of the overall, so let's just put overall reaction, is equal to the sum of all the delta H of reactions from each individual step. So in order to understand this, I think the best way to do this is through a practice question. So right here I have a practice question for you, and I'm asking you to determine delta H of the reaction, or heat of reaction, for this overall reaction. And I want you to use these individual reaction steps to do so. So if you want to try this on your own, please do so. However, if not, you can just follow what I do. Okay, so this right here is our overall reaction. So when we sum all of these individual reactions together, we want to get this overall reaction as our result. So let's start off with the first reaction here. So let's take a look at our overall reaction. So in the overall reaction, we see here that the hydrofluoric acid, the gaseous hydrofluoric acid, is on the product side. However, in this reaction, it is on the reactant side. So in order to get this hydrofluoric acid from the reactant side to the product side, we just have to flip this reaction. So let's do that. So when we flip this reaction, we will get this. Now, what happens to our delta H value? Well, all we have to do is reverse the sign of our delta H value. Well, why is that the case? Well, recall that delta H of the reaction is equal to H of the products minus H of the reactants. Therefore, when we switch the reactants and products with each other, all we're doing is we're keeping the magnitude the same, but we're just switching the sign. So that's why this number turns from a positive to a negative. So our number will become delta H is equal to negative 537 kilojoules. So let's just move this over here so we can make some more space. So let's just move this over. I'll just rewrite this. Okay. So delta H is equal to minus 537 kilojoules. But we're not done yet with this reaction here. If you look at our overall reaction, we have 4 hydrofluoric acids. However, in this reaction, we only have 2. So what do we have to do? Well, we have to multiply the whole equation by 2. So let's do this. So I'm going to get a different color. So let's do this one. Let's get rid of this 2. So when we multiply the whole thing by 2, we get 2 H2s, 2 F2s, and then 4 HFs, because this used to be 2 in front of this. So how does this affect our delta H value? Well, it affects it by multiplying our delta H value by 2, because remember that delta H is dependent on the amount of material you also have. So therefore, our delta H value goes from negative 537 kilojoules to negative 1074. So let's put that in here. So let's get rid of this one and replace it. Negative 1074 kilojoules. So that's our first step. So now let's move on to the second one down. So if we look at our overall equation, we see here that we have 2 CF4s on our product side, and in here we only have 1 CF4 on the product side. We don't have to switch this reaction, but we do have to multiply it by 2. So therefore, we get 2 CS, so solid carbon, plus 4 F2, reacting to form 2 CF4s. And our delta H will also multiply by 2 because remember it is dependent on the amount of substance present. So it goes from negative 680 to negative 1360 kilojoules. So that's negative 1360 kilojoules. So the last one is the last reaction. And we see here that the C2H4 is on the reactant side on our overall reaction. However, our individual reaction here has it on the product side. So what we have to do is switch it. And luckily, the stoichiometry here is the same as the overall reaction. So all we have to do is switch it. And that means we just have to change the sign on our delta H value. So negative 52.3 kilojoules. And now we're going to make sure that we did this all correctly. So how we make sure that we did this all correctly is by canceling out common species. So species that are both on the product and reactant side we cancel out. And we see if our overall reaction is the overall reaction that we have up here. So let's do this. So let's get a different color. Let's use green and cancel out common things. So if we look here, let's look for some common things. So the first common thing we see is the solid carbon. We have it on the product side and on the reactant side in the next one, which means that we don't need it. And it doesn't show up in the overall reaction. We also see that we have two H2s on the product side and two H2s on the reactant side up here. So they also cancel out. So what we do now is we add all of these reactions together. So let's do that. So we have C2H4, one of those. We have two F2s and four F2s, so we add those together. So plus 6 F2 gas, going to 4 HF gas, and 2 CF4 gas. And now let's make sure that this matches our equation above. So we have C2H4, C2H4, 6F2, 6F2, 2CF4, 2CF4, and 4HF, 4HF. So we did it correctly. So now what we got to do is we have to add all of our values together. So delta H of the reaction will equal negative 1074 kilojoules plus minus 1360 kilojoules plus minus 52.3 kilojoules. And when you add all of these together, you will get delta H of the reaction is equal to negative 2486.3 kilojoules. Now we have to make sure it's in the correct number of sig figs. So if we revert back to our values here, we see that we have 4, 4, and 3. And as well as up here, we have 3, 3, 3. So the maximum amount of sig figs that we can have is 3. So our delta H of reaction will be equal to negative 2.49 times 10 to the third kilojoules. And that is our answer. So that is how you use Hess's law in order to determine delta H of the reaction or heat of reaction. Now in the next video, we are going to be talking about enthalpies of formation, which is one of the last methods that we can use to determine delta H of the reaction. So I hope to see you all in that video, and I hope this helped you. See you around.